In this video, we're going to view enzymes as catalysts and ask how do they speed up reactions generally, and then how do we actually measure and quantify that? So let's get started. So in my last video, I talked about the Arrhenius relationship and how we can use it to understand what determines reaction rates. If you haven't seen it, it might be worth going back and looking at it. But at a very high level, I described K, this is the rate of a reaction, the rate constant, is as being determined by how often do the reactants collide, and then what's the probability when they collide that they actually do the reaction, they hop over an energy barrier. And I made an analogy for this with my cat, basically rolling a dice, and every time I got a 6, I gave the cat a piece of chicken. So I can ask the question, well, what's the rate that the cat gets chicken? That's determined by how often I roll that dice, and then what's the probability of rolling something that gives a chicken, in this case, if I roll a 6. So what's the probability of getting a 6? In chemical terms, we can understand this as in terms of an energy barrier, that's particularly the E part, there we go. This is the transition state energy, or the energy activation energy for the system. And we can think about it, say, for this bond that's rotating, where it's going from a low energy staggered to another low energy staggered state. It has to cross through this activation barrier of 13 kilojoules per mole to go through that eclipsed form. That's then together with how often it's trying to cross that barrier, determining the rate of the reaction. Okay, so in the rest of this video, we're going to ask how do enzymes speed up reactions? How do we quantify that rate speed up? And then what's the fastest an enzyme catalyzed reaction can even go? So let's tackle those. So first, how do enzymes speed up reactions? Now, this is one of the reasons I like the cat analogy. We can think about it in very simple terms. How do I increase the amount of chicken that goes into my cat? According to the rules of that game. And I've got two basic things I could do. I can increase the rate I roll the dice, so just roll faster. The second thing I could do is I could change the probability of rolling a chicken. In this case, it was you had to get a 6 for the cat to get chicken, so that would be weight my dice to favor 6, right? If I do either of these, I would increase the rate of getting the cat getting chicken. Enzymes have the same basic options, and it turns out they choose the second one. What they do is they increase the probability of rolling a 6 by lowering the transition state energy, right? So you've probably seen diagrams like this before, where you have the transition states was determining the reaction rate, and then an enzyme or any sort of catalyst is lowering that energy, increasing the probability of going over the transition state and thus making the reaction faster. So what determines this transition state or this activation energy? And I like viewing this in terms of probabilities, right? We said that this is the probability of getting that state. So what's making that state improbable relative to other states? And it turns out the answer is that these transition states are chemically weird, right? So we already saw this one of an eclipsed form. So basically you have these protons that are in alignment with each other. In sort of a simple-minded view, they're kind of sterically clashing rather than sort of sitting in this nice nestled staggered conformation. So it would just, the system probabilistically is going to spend more time with those bonds staggered than it is when they're up in this weird, perfectly aligned state. So that's one of the reasons, so that is one chemical transition that is weird, right? Think about an SN2 reaction you might have encountered in organic chemistry. In the middle, even if you've never seen this kind of reaction before, you can say that's a carbon. That carbon has 5 bonds. That's weird, right? So making a 5-bonded carbon, you can only do that transiently in the middle of a reaction because it's a low probability weird state. And then when we think about, say, an enzyme that's maybe catalyzing, this is a reaction we're going to talk about in a little bit, a proteolysis reaction. What happens there is you have to have I'm showing this as a base, but you have a negatively charged oxygen that's going to do a nucleophilic attack on a carbon, and then what that's going to do is create this guy here, which is called an oxyanion intermediate. And this tetrahedral intermediate is kind of in a weird state, right? We've got a formal negative charge on that oxygen, and then it's sitting in this tetrahedral form. It's going to want to go somewhere, and it's going to want, these electrons are going to want to come back and reform a double bond, and that's going to have a cascading effect elsewhere. So basically, this is an unstable state of the system because, this is an unstable state. This is an unstable state of the system, and that means that it's going to make the reaction slower than it otherwise would be. So how do you stabilize a transition state? Well, one of the ways you can do that is by creating new interactions. So This, I said, is a negatively charged oxyanion. One of the things we'll see enzymes actually do is they put partial positive charges right around that oxyanion. And that is basically a new interaction. It's going to stabilize the state, right? It's going to bring the energy down so that now it's a lower energy state. Therefore, the reaction can be faster. Okay, so generally, enzymes are going to work by lowering these transition states. They're going to interact, or lowering the activation energies by interacting with transition states. How do we actually quantify that? And so the way this is often done is using a ratio of kcat to k uncat. This would be the rate speed up, or the fold rate speed up. And this can be a really useful metric for saying how good an enzyme is, right? Is an enzyme 1,000 times faster? Does it make the reaction 1,000 times faster? 1,000,000? 1,000,000,000? And it turns out you can relate this to the change in the activation energy by the following relationship. So you've got kcat over k uncat, the fold rate speed up, is given by this, which is basically e to the difference in the activation energies over RT. Now, I've said earlier, I've said multiple times in this that I'm a big fan of math. I don't want to throw a lot of math at you in a video because it's, tedious. But I do want to show you the algebra. So what I'm going to do here is start with the one move at the beginning, and then I'm going to show all the algebra, and I'll give you a chance to pause if you want to go through and actually work through it, but otherwise I'm just going to assert that it's true and you'll have to believe me. Okay, so what I'm showing here is the relationship I showed before, that kcat over k uncat equals basically the Arrhenius relationship of one over the other. The one interesting move I can make by arranging it this way is I can get rid of that prefactor, right? Remember, that's measuring what's the probability of the things trying to collide in the first place. If we assume that that's the same for the enzyme, both catalyzed and uncatalyzed, those cancel. And that basically sets us up to do the next algebra. So basically what we're going to do is a set of log moves that I'm just going to show, and you're going to be like, I'm not following because I'm going too fast. But all that I'm doing there is rearranging terms. I'm not doing any canceling even. I'm just moving things around. But ultimately, I get down to this relationship here that says the ratio of kcat to uncat, the fold rate speed up for our enzyme, is given by the difference in the activation energies. So maybe if you want, you can pause this and, print this out, stick it on your wall. So maybe you found it, maybe you didn't. I'm moving on. Okay. One of the things that's really nice about this relationship is it lets us sort of understand the sorts of energetic changes that an enzyme needs to do to get to a particular outcome. And the overall thing we're going to find here is that a small change in the activation energy can give a huge change in rate. So all I've done here in this graph is I'm now plotting this difference. What's the difference in the catalyzed energy barrier versus the uncatalyzed energy barrier, the activation energy? And then this is the log 10 of the the fold rate speed up. So this starts down here. This is no rate speed up at all. Basically the enzyme is the same, 1 versus 1 relative catalyzed to uncatalyzed. Here it's 10 to the 12th faster. So way faster, a trillion times faster. And what we see here is we get this linear relationship that has, I've noted a couple of key points on here, and those are at minus 20 kilojoules per mole, minus 40 kilojoules per mole, and minus 60 kilojoules per mole. So if you've looked at anything in my content before, maybe you've heard me say I use minus 20 kilojoules per mole. That's a really good signpost in biochemistry. Think about it, and anybody know what that is? Turns out that's about the energy, or that is the energy of a water-water hydrogen bond. So what this is saying is if I can add the equivalent of one water-water hydrogen bond to the transition state, I get about a 3,000-fold rate speed up. If I can add 2 water-water hydrogen bond equivalents to the transition state, I can get a 10 million fold rate speed up. If I can add 3, I can get up to whatever 10 to the 10th is, right, speed up, right? So small changes in these energies, right? The equivalent here of about 3 new hydrogen bonds is going to give me a huge rate speed up. And I like this as just a rule of thumb, that 1 hydrogen bond gives you about a 3,000-fold increase in rate. Okay, so we've said how do enzymes speed up reactions? They're going to do so by stabilizing that transition state, by lowering that activation energy. We can quantify that rate speed up. It's just the ratio of the rates, or the difference in the energy barrier heights. Last thing I want to ask here is, now that we've set this up, what's the fastest an enzyme catalyzed reaction could go in principle? And so let's think about this in terms of this energy barrier. So I said that enzymes work by lowering this energy barrier. That leads to an interesting limiting case. You keep lowering the barrier, keep lowering the barrier, and now there's no barrier at all. Well, it's right. We've got no barrier associated with this reaction. So how fast is that reaction going to go? So let's go back to our Arrhenius relationship. What we have here is this barrier has now gone to 0, e to the minus 0. E to the 0 is 1, which means this whole thing goes away. And I'm left with this. So what's the rate that the reaction happens? Well, it's how often do the reactants collide? And I put this back in the cat analogy because now basically what we've done is we made it so every time we roll a dice, the cat gets chicken, right? So we weighted it so it's always either a 6 or we've changed the rule so any of the dice faces gives the cat chicken. So every time we roll, we give the cat chicken. So all that matters for how quickly the cat gets chicken is how often we roll the dice. This would be, in this case, every time that we attempt to do the reaction, it happens. So it's just how often do we attempt to do the reaction? So what determines that? What determines how often we attempt to do a reaction? So this is just a really simple simulation of two particles bouncing around. And hopefully what you appreciated is I spent a lot of time, well, sometime, I got bored. It was a very long time. And then I found the section where they actually collided. They wandered around for a long time, and then eventually they collide. And the idea here is if they collide, they react. And so what is setting the rate here is actually how quickly can the molecules diffuse into one another. What's the diffusion rate? And in fact, the fastest that an enzymatically catalyzed reaction can go, or basically any reaction, is what's called diffusion-limited. And it's any reaction whose rate is determined by how often the reactants collide, or in the words I've been using, how often they attempt to do or try to do this reaction. And it's interesting because this actually sets an absolute limit on enzyme catalyzed reactions, right? They can't go any faster than this because at some time, an enzyme can't reach out and grab onto a substrate. Instead, it's got to wait for the substrate to, find the reaction center. And you might think, well, okay, cool, theoretical limits, whatever. But it turns out there are multiple biological enzymes that are actually at this limit. One of the most important and famous for it is this one called SOD, which just has a cool name, if nothing else. It's superoxide dismutase, and it's actually really important for cleaning up dangerous superoxide radicals. And basically, it is as fast as it can go. So as soon as the superoxide radical hits, it reacts and it turns it into hydrogen peroxide in a diffusion-limited fashion. So this is a limit that cells in biology runs into. They want to make the reaction as fast as possible. Eventually, they make it as fast as they actually can without starting to, having to break new ground with physics or something. Okay. So what have we been talking about here? We've been talking about ways that enzymes speed up reactions. We've talked about this in terms of this Arrhenius relationship. So what's the rate of reaction? How often do reactants collide? And what's the probability that reactants cross the energy barrier? We've said that most of the time, the way that enzymes work is they stabilize this energy barrier, they lower it, but that in the limiting case of they've made that energy barrier as slow as possible, or as short as possible, 0, it's then determined by how often the reactants collide. So summarizing the overall ideas from this video, it would be that we can talk about things like the fold rate speed up for an enzyme. That's just going to be e to the change in the height of the energy barrier over RT. That's going to give you the rate of the catalyzed reaction over the uncatalyzed. And we've said that eventually a reaction could become diffusion limited in the case where there is no more energy barrier that's actually present for the enzyme. Okay, so that's what I got. Hopefully that gives you a better picture or a better thought process for thinking about what is an enzyme actually doing to speed up reaction rates. In the next couple of videos, we're actually going to start talking about it in terms of some little bit of arrow pushing, and then also how do we characterize molecular enzyme rates sort of in a lab context. So I will see you then.